Let's start the next chapter, which is much more into the physics now of extratropical influence on the tropics, but we are still talking about waves and simplified basic states with one example of a real cross-section of the basic state. And we'll see the basic questions we have not answered yet. Do the highly energetic extratropical transients influence the tropics? So we haven't done much mid-latitudes, but if you just imagine a parcel of air that's being transported from the equatorial region to high latitudes, those who know the basic physics may already know that you end up producing incredibly fast zonal speeds if you want to conserve angular momentum, which is not possible. So obviously angular momentum conservation breaks down and you end up with baroclinic instabilities in the mid-latitudes. And then there are features like the storm tracks, which end up with lots of breaking Rossby waves and other eddy features that are very energetic, so they can create perturbations. Then the question is whether those perturbations project onto waves and propagate into the tropics. Because the question of Charney's, where he assumed this by scale arguments that the tropical flows of 10 to the 6 meter scale tend to be barotropic, and he added one solution where he said if convection can reduce static stability, then you can end up with baroclinic processes and communication between the lower levels and the upper levels, right? But we know that generating just these disturbances within the tropics depends on the wave propagations, energy accumulation, trapping in the horizontal, vertical as well. The other idea would be by Charney himself also to see if the extratropical disturbances can affect the tropics and create disturbances, because we still haven't explained where the convection comes from. To reduce static stability, you need convection. Can that be triggered from the extratropics? The other question is, do the extratropical disturbances of one hemisphere influence the extratropics of the adjacent hemisphere? So we'll look at these things by looking at lateral wave propagation. Again, idealized basic state. So we'll start with a zonally symmetric base state. Zonally symmetric, in case you don't already know, basically means at least over the scales that we are worrying about, the zonal derivative is zero. For example, du bar dx is zero, and you can have meridional shear but not zonal variability. The derivation of the potential verticity equation for the mid-latitudes on an extratropical beta plane is given in Appendix H. I will run through it here. So you write the pressure, density, potential, temperature, and the vertical state equation, or the vertical structure stratification in terms of these functions: surface pressure plus a function, background density plus a function, background potential temperature first variability, and reference density decaying exponentially with height, given the scale height, which is RT bar over G. We have seen these already several times. So we write the total winds U and V in terms of a geostrophic component and an ageostrophic component. So we have the geostrophic relation plus the ageostrophic part, and similarly for the meridional winds. Of course, in these cases we still have very strong geostrophic constraints, so the geostrophic winds are much greater than the ageostrophic component. With that, you can solve for the verticity equation, which is the d dt of the total verticity, so geostrophic verticity plus the planetary verticity on the beta plane, which is beta y, plus the advection of the planetary verticity, or the divergence, sorry, and convergence of the planetary verticity. So we are still talking about stretching and compressing air columns to look at verticity conservation. And the geostrophic vorticity is of course written in terms of this perturbation pressure function that we wrote before. ddx, ddy are the geostrophic velocities, and vorticity is ddx of the velocity minus ddy, or ddy minus ddx, which you plug in and you get d squared x squared and d squared dy squared, and remember there is the minus sign in the zonal equation, so you end up with this. Right? Very easy. You can revise it, go back and revise it from the basics if you wish. Okay, so the vertical equation now written in terms of the potential temperatures, the continuity equation including the W in pressure coordinates, as we will do in a minute. We are still in the XYZ here. So you have the thermodynamic equation with the vertical modification of theta s caused by either perturbation velocity or heating, that we will not talk about explicitly here because we're writing the potential vorticity equation for an adiabatic situation. You can then define a stream function of the geostrophic wind, which will give us a new version of this vorticity equation, the horizontal part with the vorticity in terms of the stream functions derivative in the vertical, plus this stability term, so the vertical advection of the atmospheric stratification. Okay, that basically results in the changes in the static stability and results in vorticity changes as well. Okay. You can write that as ddt plus ug ddx. So this is our d, small d dt term, or the material derivative in terms of the stream function, plus the planetary vorticity term. And n squared here is of course the static stability, Brunt-Väisälä frequency. And we can eliminate the divergence term between H5, so these equations and these equations. I'm not going to go through it in detail because you can look it up in the appendix, plus I want to focus here on the physics. So we end up with this vorticity conservation equation where V tilde is got an expression, and here Q geostrophic is d squared psi dx squared plus d squared del squared psi del y squared plus beta y plus this term here. For simplicity, we will assume that values of the Brunt-Väisälä frequency n squared and the vertical scale height relation is constant. And to study the propagation of equatorial modes towards the equator in a zonally symmetric basic state, we will split the stream function and the horizontal geostrophic velocities into a mean and a perturbation, which is what we have always done when we want to look for wave solutions, right? So maybe I can leave it here, but let me just add this, that we can write the vorticity equation now in terms of these split between the mean and the perturbation. So we have the QG prime term based on the geostrophic basic state, advected around by the geostrophic basic state, the planetary vorticity, which depends on advection in the meridional direction, so V prime, and you have the advection and the time derivative term of this relation, which is beginning to look like what we have seen before, right? We will see in a minute. And the beta d psi prime dx term, where we are going to assume that psi prime xy xt is a function of gamma z, which obviously goes back to the stability relation, psi yz, and exponential ik times x minus ct. So here c is the zonal phase speed of a wave, gamma z is this function, which is related to the vertical stability and the Brunt-Väisälä frequency, which allows algebraic simplification. So we can write this equation which has solutions of this form. Obviously we have to look for oscillatory solutions, and we'll see that there are also decaying or external solutions, which I'll come back to. This is a fairly long one, 10 minutes, not too bad, but I rushed through the equations because we will just get to the solutions in a minute. So remember, again, in this chapter we're going to look at the potential for extratropical perturbations to influence the tropics, and see if we can relate that to signatures of convection in terms of vertical motion and outgoing long wave radiation. Remember, where there is deep convection, OLR tends to be minimum. So if we can see under what conditions the extratropical perturbations propagate into the tropics, and under what conditions they generate a OLR and vertical velocity signal, then we can say something about Charney's idea that maybe convection in the deep tropics can be triggered by influence of the extratropics on the tropics. We are broadly saying extratropics here. We will see the range of latitudes when we look at specific solutions. Okay?